Today our note is about related angles on the Cartesian plane. So we've already learned about understanding angles on the Cartesian plane, but now we're going to go further and get a bit more depth of our understanding. So I know this is a bit of a long paragraph to start with, but let's take a look at what it says. Trigonometric ratios, so that means sine, cos, and tan, are used to model many real-life scenarios. When solving problems involving trigonometric quantities, there is almost always more than one solution, sometimes an infinite number of solutions. It is important to find all possible solutions and then select which solutions are appropriate. Okay, the multiple solutions comes from, again, going around a circle and being able to hit a terminal arm many times. It is useful to express angles on the Cartesian plane. As the terminal arm creates angles in the positive direction, this way, a circle is created. So as you're going around like this, a circle is created by those angles. It has a radius that we'll label r. As the terminal arm rotates around the circle, the coordinates of its endpoint can be expressed as x, y. So as you take, a point around the circle, any point x, y, the x and the y will change as you go around the circle. So let's take a look at this example. The point 3, 4 is on the terminal arm of an angle in standard position. So remember, standard position means that the initial arm is on the positive x-axis, okay? And we're going in the positive counterclockwise direction. Sketch the principal angle and create expressions for the primary trig ratios. Find the value of the primary angle. So I just already plotted the point 3, 4, so 3 this way, 4 up. And then you can create this as a terminal arm. And so theta would go in this direction and can be labeled as such. Now, to use SOHCAHTOA, we need a right triangle. So we need to create a right triangle here. So what we can do is drop a vertical down from the point 3, 4 until it hits here. Okay, and we can label that as a right triangle, where this is theta. So in order to find our sine, cos, and tan, we need sine of theta is opposite over hypotenuse. So in this case, what's opposite? How long is this line? Well, we know that this is the point 3, 4, so the length of this is 4. But how do we find the length of the hypotenuse? Well, this length is 4, we know that this length is 3, and since this is a right triangle, we can use Pythagorean theorem to find r. So r squared is equal to 4 squared plus 3 squared, okay? When we solve this, we find that r is equal to 5. You might also recognize the 3, 4, 5 pattern from right triangles. So therefore, we know that the opposite is 4, and the hypotenuse is, in this case, 5. Okay, so for cos theta, cos is adjacent over hypotenuse, so our adjacent length is 3, and our hypotenuse is 5. For tan, it's opposite over adjacent, TOA. Adjacent, I said adjacent. Adjacent. And so our opposite is 4, and our adjacent is 3. Oh, tan theta. Now to solve for theta, we take the inverse of any 3 of these trig ratios. So you can choose sine, cos, or tan. So I'll just choose sine. So theta is the inverse sine of 4 over 5, and you put that into your calculator, and you get about 53 degrees. So there you have it. Okay? So take a look at this example. It's the most basic example, and now we're going to take this example and create a general definition of sine, cos, and tan on the Cartesian plane. All right, so normal triangle where it's not on the Cartesian plane, just a plain old right triangle, and where theta is the unknown angle here, we would say that this is opposite, this is adjacent, and this is hypotenuse. So sine theta is opposite over hypotenuse, cos theta is adjacent over hypotenuse, and tan theta is opposite over adjacent. So ka toa. But how can we take this understanding and extend it to the Cartesian plane? So in this case, we have, let's any point on a terminal arm can be labeled as P, where it's the coordinates are x and y. And we can drop down a vertical line to create a right triangle. You'll see that this looks just like that right triangle, and we label theta here. So it goes from the initial arm to the terminal arm. So in this case, this length is however long x is, so we can label it x. This length is however long y is. And this length is the radius of a circle that would be created, so we'll label it r. But remember that r can be found by finding the square root of x squared plus y squared. That's just Pythagorean theorem because it's a right triangle. Okay? R squared equals x squared plus y squared, so r is the square root of x squared plus y squared. So make sure you get this down. So, knowing all of this, we can find a new way of defining sine, cos, and tan on the Cartesian plane. So, SOHCAHTOA, so is normally opposite over hypotenuse. Well, here that would just be y over r. Cos would then be x over r. And tan would be y over x. So if you're given the coordinates of a point anywhere on the Cartesian plane, you can find its sine, cos, and tan ratios by using the y and x that you're given to find r, and then placing y, x, and r into any of these ratios. That also allows you to find the related acute angle by performing an inverse sine, cos, or tan operation. So this is something you should take a look at before you move on. You might want to pause the video to make sure that you fully understand where we're getting the y over r, the x over r, and the y over x from. This will continue to be important throughout this chapter and the next. Okay, so this also leads to another conclusion that any point xy on the circle of radius r and rotated through theta can be expressed in this way. Instead of x, you can write r cos theta, and instead of y, you can write r sine theta. This is because cos theta is equal to x over r, so if you just rearrange for x, you get r times cos theta. Same thing here. Sine theta equals y over r, and if you solve for y, you get r sine theta. So let's continue example 1. What if we have now the point -3, +4 on the terminal arm? So we can draw that coordinate, -3, 4. All right, so I drew that on the Cartesian plane. And then I labeled theta, and I called it theta 2, and that's the principal angle with the terminal arm that contains -3, 4. So what are its primary trig ratios? That's what we need to figure out now. Okay, so we can create a right triangle here, okay, where this is -3 here, this is 4, and if we do Pythagorean theorem again, we'll find that this is also 5, this radius. So here we have the related acute angle. Okay, so when we're looking at this triangle, we'll label this interior angle as the related acute angle, which we learned last lesson. So sine of theta then is equal to 4 over 5 again. But cos of theta is now equal to -3 over 5. Okay? Tan of theta, sorry, they should all be theta 2. is, remember it's y over x, so that's 4 over negative 3, which we'll just write as negative 4/3 and make the whole fraction negative. Okay? So that means that since this is the same relationship as we've had before, that beta is equal to 53 degrees. So how do we find how big theta is? Well, theta 2 is just equal to 180 degrees minus 53 degrees. So it's 127 degrees. Okay, so there you have it. You actually have to use the related acute angle to find this 127 degrees, okay? If you find the inverse sine of 4 over 5, if you put that into your calculator right now, it will give you 53 degrees. It won't give you 127 degrees. So your calculator helps you find the related acute angle, but you have to use your knowledge of the Cartesian plane to help you find the actual principal angle. So we're going to continue now into quadrants 3 and 4. So I invite you to try these two quadrants without me. So I invite you to pause the video and try these two in pencil, and then to resume the video and see if you did it correctly. So complete the above tasks for these 2 points. So we label our our principal angle here, and we'll label it theta 3, okay? And our related acute angle is right here. Remember, it's always between the arm and the x-axis, so it's not here, okay? So in this case, here's our right triangle. This is negative 4, this is negative 3. So sine of theta 3 is y over r, so negative 4 over 5. This is still 5. Okay? Cos of theta 3 is x over r, so negative 3 over 5. And tan of theta 3 is y over x, so negative 4 over negative 3, which actually gives a positive ratio of 4/3. Okay? Our beta is again going to be equal to 53 degrees. So theta is 180 plus 53 degrees, so 133 degrees, rounded, okay? So if you find the sine of 133 degrees, you should get about negative 0.8, which is negative 4/5. If you take the cos of 133 degrees, you should get negative 0.6-ish, because we rounded. And then if you take the tan of 133 degrees, you should get positive 1.333 approximately, okay? Or about 4/3, all right? So again, it's the same related acute angle because the quantities 4, 3, and 5 are all the same. It's just the fact of whether they're negative or positive that's different. So the fact is if they're negative or positive will tell you which quadrant they'll be in, but if they all have the same ratio, so 4 to 3 to 4 to 5, it's the related acute angle that will be the same in any of the 4 quadrants. So here's 3, negative 4. So our principal angle is here, theta 4. And our related acute angle is here. All right, and we can label our right triangle. Bring this up here. Okay, so this is 3 now, and this is negative 4, and this is, again, 5, which you can use Pythagorean theorem to find that. So sine of theta 4 is y over r, so negative 4/5. Cos of theta 4 is 3/5, and tan of theta 4 is minus 4/3. Okay, theta 4 is equal to 360 degrees minus 53 degrees, which is 307 degrees. Okay, so there you have it. All right, so what do the points P, Q, R, and S and their related acute or the related angles have in common? Well, they're all just variations of the points plus or minus 3, and plus or minus 4. So they're all just different versions of that coordinate, okay? And they all have a related acute angle of 53 degrees, okay? So they all share a beta of 53 degrees. And their sine, cos, and tan values are all the same. They're just negative or positive versions of each other. So they all have the same value, like the absolute value of sine. It just might be a negative or a positive. So their values are the same, but they could be positive or negative, okay? What is different between P, Q, R, and S? Well, the principal angle is different. Okay, that's the principal angle. That is what is different in all three.